All right, so let's start going through the examples that we weren't able to get through together in class. So for number 2, we're going to be going through and trying to do the same things. So I didn't specifically write down here what steps you need to take, and because I want you to start thinking about just naturally picking these things out. I am, though, going to go through and do just like we did in the last example and just try to pick out as much as possible. Okay, so the Pepsi Challenge is an ongoing marketing campaign run by Pepsi since 1975 in which they do a blind taste test of 2 sodas, so Pepsi and Coke. So we've done a problem like this before, right? We've got to try to remember previous problems we've done. We had this setup, Pepsi versus Coke, before. And so it sounds like we're doing the same thing. So let's keep going. So participants do a blind taste test, so people, and they select their preferred soda. Okay. Pepsi claims that 3 out of every 5 people prefer Pepsi. We take a random sample and get results. So, remember how this worked previously. This is telling me that I'm dealing with a categorical variable, right? Because I'm giving each person a choice, right? Each person, here I am, I have Pepsi or Coke. There's 2 choices, you pick one of them. So that's categorical. So then immediately, if I see that, I'm thinking, okay, I want pi, I want p hat. These are my symbols that I'm going to probably want to use. So I got categorical data. Okay, so great, we picked out some of that. Now let's keep going, because once we've got this, we also have to be thinking, all right, there's a sample, somewhere there's a sample, and somewhere also there's a claimed proportion that I should be trying to test. So see if we can find the sample, and just look for it. A random sample of 140 people is taken. So my sample is 140 people, okay, that we talked to. And then that's enough just for the sample, but you can keep going with this if you want. What happened with those 140 people? 92 chose Pepsi. So from the sample, we get 92 out of 140, which is our p hat, chose Pepsi. And so we found our statistic. Remember, the statistic is a number that comes from the sample. It tells you about the sample. What happened to those 140 people? 92 of 140 chose Pepsi. Okay. So then, this is a pretty good start, but you might also be thinking like, well, I keep doing hypothesis testing and I got to pick a number from that. So where's that going to kind of come from? Well, so we go back here, and I think it's very natural here to just go, 2 choices, 50-50. I'm all done, 0.5. But there's an extra piece in here. Claim. We got to look for this word claim. Pepsi claims that 3 out of every 5 people prefer their brand of cola. If you give me a claim, I'm thinking that's what I want to test. So 3 out of 5, that's going to be my claimed value. We're going to need that in a second. Okay, so when we're doing this, let's first say, okay, what's my population? This is my big group that I'm trying to learn about. If you're stuck here, remember, go to the sample, 140 people, okay, and then population, that's the big group. So the population is the big group out of where the sample comes from. So if you're comfortable saying the sample is 140 people, okay, then the population is just what's the big group they fit into here. Who are we trying to learn about, right? So we are trying to learn not about the 140 people, but we're trying to learn about all people. So the population would then be all people who drink soda. And I added this last piece because we have to think a little bit about this. It can't just be all people, because the only people we're going to get to do this are ones who drink soda. If you don't drink soda, you're not going to be doing the Pepsi challenge. You're not going to drink the soda. So we have to be a little more on this, a little, careful on this. Not only does Pepsi only care about the people who drink soda, because that's who's going to buy their product, but that's also where the sample's coming from, right? These people, I'm going to come up to them and I'm going to say, which one do you like? And they're going to say, I don't like soda, get out of my face. That's not the situation. So we're only looking at the big group of people who are drinking soda, who like soda. Okay? Or cola, depending on where you live in the country. Sorry, my New England preference was coming out there. So soda, cola, or pop. I guess that's pop. That's something you could say too. So that's my population. Now, parameter. What do I want? What number can I describe that would help me answer this question for Pepsi, that I could calculate if I could go talk to the whole population? And again, this might be tricky, but you can use some of the stuff you've already thought about. Pi p hat. That's a proportion. You say pi, you say p hat, you immediately are going to be writing proportion for your parameter. So remember, there's only two choices. In this case, because of the symbols you picked out, this should be the proportion of, and then it's always proportion of blank. Well, it's the proportion of the population of soda drinkers. And what are we interested in for these soda drinkers? What are we trying to figure out? Well, go back to this idea. We were thinking about this. We are asking if they like Coke or Pepsi. Pepsi, the company, wants to know what proportion of people like Pepsi. There you go. The proportion of soda drinkers who prefer Pepsi. If I could know this number, this is a number here, right? It's a proportion. If I could know it, Pepsi would know everything they need to know here. So remember, what's the parameter? It's either a proportion or a mean right now, and it's something that you can get from the population that answers the question, answers the idea behind the problem. So that's a couple ways you can think about this. And of course, we already said it, the symbol is pi because it's a proportion. So this is pi. Okay, so we've got the setup then for our hypotheses. So the null and alternative hypotheses. So let's do it. Symbols first. All right. So you already told me pi, pi, pi. This is always equals. And then we just need the number here. What is the claimed proportion of soda drinkers that Pepsi's saying prefer Pepsi? What proportion did they say? Oh, found the word claim here. 3 out of every 5. Which is 60%. Pepsi is claiming 60% of people prefer Pepsi over Coke. Okay? So then we go back to the problem and we say, do I have any idea if this number really should be lower, higher, do I, or just different? And what am I trying to test here? I'm always trying to test the claim. And the way I do that is by saying, do I have evidence that it's different than what Pepsi's saying to me? But I don't see anything in here that says I personally think it's more or less than their claim. I'm just trying to see if it's different. So because of that, not equal to, which is again just 0.6. All right. So if you want to put this in words, you can do that. Remember what you do. You just take your symbols. Pi, write it in words. You already wrote that in words. If you picked out the parameter, you already wrote it in words. So your sentence then could be the proportion of soda drinkers who prefer Pepsi. And then what did we say for equal sign? Equal sign becomes the word is. And then you put your actual value. 0.6 would just be 0.6. You could do 3/5, that's fine too. Same number. What changes? Remember how we talked about this. Let's go purple. Not equal to here becomes is not. And then, of course, the number does not change. because it's always the same. And then again, the symbol doesn't change. So you could just write in the same sentence here. I did not leave myself enough room for this. This exact sentence, this parameter, you can just drag down here and plop into this. Boop. Drag it down here too. You don't have to think too hard about this. If you've already done the parameter, you've already done this. The only thing is you just have to say is the number, or, and for the alternative, you have to pick out the right word here depending on the symbol. In this case, is not, and then the number. Done. Okay, well, so then we actually got to get to testing this. So we did pi, which means we need the one proportion applet. So let's jump over to that. So here we are at this applet. Remember what we have to do. We go here and we look at our null hypothesis, and the first box we put it in, 0.6. Then we go down here and we say, okay, what was our sample size? Well, 140 people. That was our sample size. And then we go and we type in the number of samples, 100, 1,000, whatever you want. All right, we get our picture. Go ahead and hit summary stats. And then don't forget proportion of successes. You can do number of successes, but I think proportion of successes is a little bit nicer to work with in general, because then it connects back to your hypotheses really nice, because 0.6 is supposed to be in the middle, so oh yeah, that looks right, and then we get the standard deviation. So let's bring this over so we have it to work with. Okay, we've got our simulation here, and so again, this is not a step that I'm specifically asking you for here or did above, but we know how to look at this and try to see if our statistic is usual, unusual, just kind of right off the bat. So we go back up here. 92 out of 140 was our p-hat. So let's write that here, just remind ourselves. Okay, and so we put that in our calculator so we can get this as a fraction that's a little bit, or a decimal, sorry, that's nicer to use here. This ends up being 0.657. And then I rounded a little bit there. Okay. Well, on the picture, we can go try to find this. Again, this is just us kind of looking at it. It looks like maybe 6.4 is here. 6.5, 6.6, 6.7, 6.8. That's about right, it seems like. And so we're about 4, 5, 6. It looks like our p-hat is right here. That looks like where our p-hat is. And so it's a little tougher. This isn't quite as clear-cut as they have been in the past, usual, unusual. My gut reaction is that this is probably a usual statistic, just from doing this more often. But I'm not saying that you have to be able to kind of just snap your fingers and do that. That's what we have the p-value for, right? The p-value is what does this for us. So let's go get that p-value. So you've kind of checked it out. Now let's get the p-value. We'll do that down here. All right, so let's do the p-value now. And the p-value, remember, we're just going to go find our statistic on here, and then we're going to count all of the dots at that point or more extreme. So let's do it. All we have to do is we go over here, and we type into this box our statistic. So you got to go back up to your problem, and wherever you wrote it down, that's where you got to bring it from, 0.657. All right, that was our 92 out of 140. And then remember, you got to go to your alternative hypothesis, and you got to say, okay, less than, greater than, not equal to. If it's just less than or greater than, you can just switch between these two. But if it's not equal to, then you can be on any of these, doesn't matter, and you can hit two-sided. Once you do the two-sided, scroll back over, there you go. It'll give us our two-sided p-value. All right, so we see the picture here, and then specifically we get our p-value. So I'm going to copy this all over into the document so we can see the whole thing. Okay, so our p-value is right here. So specifically, the p-value is equal to 0.205, which is, if you want to convert, 20.5%, depending on how you want to look at this. So remember, just start off process. Process, we immediately say, okay, what's our significance level? Because we've got the p-value. Then you want to actually figure out what's going on here. So you go, the significance level, well, in the problem it doesn't say anything, so it's 0.05. But if it was something different, we could still talk about that. If it was 0.1 or 0.01, any of these we could use them. And here's how we do it. Remember, you take your p-value, and either you are less than the significance level, so this is scenario 1, so your options, you're less than alpha, right, which means that your statistic is unusual, or your p-value is bigger than or equal to alpha, which means your statistic is usual. Okay, so what's our alpha in this case? Well, 0.05, we can start with that. So then all we have to do is we say, okay, 0.205, that's our p-value. That's actually bigger than or equal to 0.05. Right? 20% is bigger than 5%. If you'd rather do this in percentages, you can do that. Maybe it's easier for you to see. This is true. So then that means our stat is usual. We have usual statistic. So what we have to remember is, once we get that, that means we can start saying things about the conclusion, the hypotheses. The goal is to remember talk about the hypotheses. Let me give myself some more space here. Oh, don't you go anywhere. So then remember, from this, because our stat is usual, or if you want to say because our p-value is greater than alpha, we can say, conclusion, we can say that the null is plausible. And then you want to bring it into context, right? Bring it in context. Context then says, well, what was the null? Go back up and just read it off. The null said that the proportion of soda drinkers who prefer Pepsi is 60%, 0.603 So how can we say that? It is plausible that 60% of soda drinkers prefer Pepsi over Coke. Boom. Now you'll see that I actually kind of did that differently than in class. In class, I just literally took the null, wrote it out exactly, is plausible, and we kind of just put that in there. But I flipped around the order. I wrote plausible first, and then I wrote in what the actual parameter was, pi. And so it just sounded a little better to say that. And that's your flexibility with this. You need to tell me the null is plausible, for sure. And then in context, you need to just bring that, you're like, what is the null? You got to bring that from the problem. But then you have to write it in a way that sounds like something you would say. This is how I would say it. It's plausible that 60% of soda drinkers prefer Pepsi over Coke. Based on the sample, I don't have enough evidence to say it's not 60, so I'm saying, okay, 60 is plausible. This is not me running around saying Pepsi over Coke, Pepsi over Coke. I'm not saying I've got, strong evidence for this. I'm just saying that based on the one sample you gave me, I don't have any strong reason to believe that this is incorrect. And that's a tough thing, I know, but that's an important distinction to make there. So there you go. That's the full kind of problem you could do, and I could give you. And again, I wouldn't necessarily give you all of these pieces, right? But they're all still important. Most of the time, you're just gonna, if you were kind of going quick through this problem, you'd set up your hypotheses, you do a simulation, p-value, conclusion, done. But it can still help when you're still trying to figure some of this out to try to go all the way back through. What's your population? What's your parameter? What's your sample? What symbols should I use? Like right at the beginning. That's all helpful stuff to do. All right. Okay, so in example number 3, we are looking at this example with the United States Health and Human Services Poverty Guidelines for 2017. Okay, so in March 2017, a PBS report stated that approximately 8.3% of all citizens live below the poverty line in the U.S. So again, right here, we're getting some claimed value. So this is a claimed value here. Some big national numbers being said to us, 8.3% for everyone. And then we say, okay, well, a study is conducted to determine if a larger proportion of New York State residents live below the poverty line. In a random sample of 1,000 residents, it is determined that 11.31% were living below. So a couple things here. Percent, proportion. What does that tell me? I'm using pi, I'm using p hat here. I should be saying the proportion of something in some of my answers. Okay. I also can pick out my sample. I did a sample of 1,000 New York State residents, right? Okay. And then, well, what happened with this sample? 11.31% of them are living below the poverty line. So that's my p hat because it's my statistic. It comes from the sample. Okay? So we can write this as 0.1131. It's a little more useful way to write it for the applet. And then we could just go from here. So we're going to kind of skip forward with some of these steps a little bit so you can try to fill in the details or ask me if you're not sure. So I'm going to write the hypotheses out. Pi, because again we're a proportion. And then what goes here? My claimed value for the whole big population that I'm trying to compare to. So this was the one that was true for all the U.S. I'm interested in what's going on for New York State. Right? So, but I want to compare back to that. And then for the alternative, what are we looking here? To determine if a larger proportion. So where did that come from in the problem? This symbol here came from the larger proportion. So I'm seeing if I can find evidence that New York State is different than the whole country by looking specifically in New York State. So I'm trying to compare New York State to the big whole country. Okay, so once you get those hypotheses and you know it's pi, you can run your simulation. And then we'll find the p-value and just all these same steps over and over and over again. So let's jump to the simulation. So at the simulation, and remember how this works, probability of heads. You put in what you have in your null hypothesis. Number of tosses, 1,000. That's your sample size, right? We wrote out that sample earlier. Then we could do 100, 1,000, doesn't matter for the number of samples. So we're going to hit draw. Okay, so there's our nice little picture. It looks to be centered pretty close to where we said it should be, 8.3%. Great, okay. And then we've got the spread here, the standard deviation. So we're just going to skip the step of kind of just having this piece in and go straight to the p-value idea. So remember how this works. We take our statistic, 0.1131, right here. We put it in the box, and then we match up our hypotheses. Greater than, greater than. Awesome. Hit count. Make sure this does not say two-sided because it's not, right? It's just greater than. Okay. And there you go. Our p-value is here. Our p-value is here. So let's put this on the sheet. Let me take a screenshot real quick. Okay, so our p-value is given to us right here, 0.0020. And so what do? Now we compare to alpha. This problem alpha is not said specifically, so that means it's 0.05. So what happens? We say, okay, p-value, if it's less than alpha, we're going to support the alternative. On the other hand, if our p-value is bigger than or equal to alpha, we're going to say null is plausible. Right? Our only two options here. So let's just write in the numbers. 0.002 is less than 0.05. That tells me, based on what we just wrote down here, that I support the alternative. And so if I go back to the problem, what did we write down for the alternative? The proportion of New York State residents living below the poverty line, we believe that that's greater than the national average of 8.3%. So let me write that out in the sentence. We have evidence that, and you can switch things up. You don't need to say proportion. You can say percent here, and that I think sounds a little bit better. We have evidence that the percentage of New York State residents living below the poverty line is greater than 8.3%. So we think, based on the data we have, that New York State, overall, we're doing worse than the national average. Right? There you go. That's it. Get your hypotheses. Make sure you're dealing with the right symbols here. Pick out your sample. Run the simulation. Get your p-value. Compare to alpha, your cutoff. Tell me what's going on with your conclusion. And that's it. So let's try the next one. The Center for Disease Control, the CDC, determined that the average life expectancy for the U.S. population in 2018 was 78.7 years and gave a standard deviation. So, average life expectancy, 78.7 years, that's time. Okay, that sounded quantitative to me, but we can still keep reading. Another piece, though, they gave a standard deviation, too. Remember, quantitative data, that's the one that has a mean and standard deviation, where categorical is only a proportion, just the one piece. So it's making me think quantitative, but we can keep reading. After learning this, you decide to collect data from a random sample of New York City obituaries from 2018 to 2020 to compare the life expectancy of New York City residents to the big U.S. life expectancy. Because we want to know, New York City residents tend to live longer or shorter lives compared to the national average. This is a key piece here, right? This is not us saying we know one or the other. We're saying could be either. We don't know. So keep that in mind for a little bit later. We take a random sample of 18 obituaries and find an average age to be 82.1 years. So let's pick out some of this information. We saw the word average a few times. We saw years was something we measure in time. So we got a good feeling here that our symbols are mu and x bar for this problem. Okay. All right, well, so also it says sample. We got to pick out this sample. So that's our sample is 18 obituaries. And so, each obituary is a person. So you could think also 18 people who have passed away. That's also kind of the step you can make too if you want to focus on people, because it's average life expectancy for a person. So this really tells us that we looked at 18 people. Okay, because knowing how old they lived to, that's giving us information about life expectancy. So I don't know how long they lived. So we got that, and then specifically, what did it tell us? The average age is 82.1 years. This is my statistic. X bar is 82.1 years. Again, it's not a proportion. Don't have that information. It's not something out of something else. It's just an average time given. So, at this point, we can do our hypotheses. We're geared up for the hypotheses. So let's scroll down so we can get to that. Well, it was an average mu, always equal. And then remember, not from the sample, what are we comparing to? We're comparing to 78.7 years. So what does this first line say? This first line says the average life expectancy of New York City residents, average of all New York City residents, is the national average. Or the alternative is actually the average life expectancy of New York City residents is not the national average from the CDC. It's not. Those are two options. Okay. So once you set that up, then remember we've got to set up the distribution. So we're using a different app though. This is because we're doing the mean, we're using the one mean app. So let's jump over there. Okay, so we've got this app up. Now remember, things are different with this app. We've got to provide much more information than the one proportion applet. So first off, what's the population mean? Well, that's not too bad. It's just like the other applet. Go grab what you put in for the null. Okay, what's the population standard deviation? Again, that's given right here, 6.5 years. There it is. Now, the population shape, this is kind of hard to figure out exactly what this should look like. You can try to think through some different things here, but if you're really not sure, I think you could convince yourself that this might be normally distributed. Most people are near the average, some people older, some people younger. So let's hit set population. And then we've got our population for the computer. You hit show sampling options. And then this goes back to our other applet, just like that. Number of samples, 100,000. Sample size, how many people did we talk to? We didn't talk to anyone, right? We looked at 18 obituaries. So that was 18 people that we looked at how long they lived. Draw samples. Okay. And remember, we don't care about this picture. We only care about this picture, our distribution. And we get a mean, a standard deviation. Okay, so we got a nice little picture going. That's good. We got everything where we want it. So then remember, we got to do the p-value. How do we do that? Well, we take our statistic, 82.1. That's what came from our sample. And then we got to pick the right symbol. Greater than, less than, beyond. What do we say? Greater than, less than, or just beyond, meaning both sides? Well, we did not equal to, so that's beyond. And see how it colors in both sides. Important, right? See how it colors in both sides. Okay, so what does the applet do? It counts up all of the simulated samples that are just like our sample, but simulated assuming the CDC national average. And it finds that 30 of them were as extreme as what we got or more extreme. And that's just exactly our p-value. So let's grab this and put it on the sheet so we can talk about it. Okay, so we've got our p-value here. So I'm going to write it up top so we can save ourselves some room here. So we got our p-value is 0.03. All right. So then what do we do? Compare to alpha. Now we're actually going to do two different alphas here so you can see what happens. And I want to talk about it a little bit. Alpha equals 0.05. If that's your cutoff, which in this problem you can assume since it's not given, right? Then what do? We say, okay, compare. Our p-value is less than alpha. That's true. So that tells us support the alternative. All right, so this is telling me that I've got evidence that the average life expectancy of New York City residents is not the CDC national average. I'm not saying specifically bigger, less. I'm not saying that. I'm just saying I don't think it's this number. All right, I've got enough evidence to say that. Now, what if, so not this problem the way it's said, but what if alpha was actually 0.01? Run the process. Take your p-value, less than 0.01. Oh, it's not. That's not true. 0.03 is actually bigger than or equal to 0.01. This tells me null is plausible. So we got to be careful here. Depending on the alpha we pick, we could get two different conclusions. And that's because alpha is you picking out, and you usually do this at the beginning of the problem, you picking out at what level do I have to get to convince me to go with the alternative? How much evidence do I need in order to assume the null is true and then see that evidence and go, okay, I support the alternative. You've convinced me. Alpha is your cutoff for being convinced to go for the alternative. The smaller you make alpha, see how it got smaller here? The harder it becomes to convince you to the alternative. So a person who has a smaller alpha, when they come to a problem, that person is going to be harder to convince that the alternative is what's happening. Right? They're not going to reject the null unless you give them a lot of evidence. That's what this small alpha is doing. So you can see then that depending on your alpha, which we talked about previously, like why we would want to pick different alphas depending on the scenario, the jury example, you can get different conclusions. Here, this p-value is small enough, we say, okay, there's enough evidence based on my alpha where I'm going to say I'm comfortable rejecting the null, going for the alternative. I'm comfortable at this level being wrong here about this. But if you come up with an alpha that's 0.01 and you get that same sample, same evidence, same p-value, you set up this alpha at the beginning and you're saying, you know what, this is just not quite enough evidence for me to reject the null. I'm not quite convinced enough by this evidence to say I don't think that it's the CDC average. Null is plausible. So that's what alpha's doing. It's giving you that cutoff that you got to hit this bar with your evidence or I'm not going to go for it. That's what alpha's doing. Okay, so there you go. That's your idea for those types of problems. So what was the overall process? Pick out the information. Get your symbols. What was your sample? What's your statistic? Right? Just to kind of get through that at the beginning of the problem. Then you can set up your hypotheses if you're comfortable jumping to that. You may want to keep practicing what's the population, what's the parameter. But once you get pretty comfortable there, you can just jump to the hypotheses. Put your simulation through, do your simulation, get the p-value, and then compare it to alpha to make your conclusion. You know, it's not nothing. There's a lot of steps there, but we just got to get this process, boop, 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 down, down, down. Each piece, get the piece, get the piece. And then, you know, we'll keep talking about what this means as we go through. What each step, we really got to understand what it means. But right now, just get the process down. Okay. So, in class, we worked on number 5. So the last thing we didn't do with number 5 is usual, unusual. So I'll just add this in here. We got a standardized statistic of negative 1.9375. That's just shy of negative 2. And remember, if our statistic is inside the negative 2 to 2 range, if you are in this box, right, then you are a usual statistic. And even though we're right at the edge, we are in the box. So our statistic is usual. And that's it. Boom. Just like the 2SD method. It's very, very similar setup. Just like the 2SD method. Okay, so we got another one of those. We're going to try to do the same thing as we just did. A New York Times article said they were investigating the average commute time. Average and talking about time. Quantitative sounding. workers in major cities found that the longest average commute time for workers in New York City who traveled an average of 35.9 minutes each day. Okay, so we have an article looking at this, claiming a specific average, giving a standard deviation. This is a giveaway. You tell me that there's a standard deviation, I'm thinking, okay, this has got to be quantitative. So seeing average, seeing time, seeing another average given with a standard deviation, these are all telling me this is an X bar, this is a mu problem. I'm quantitative. So we live close to New York City, and we know people from in the neighborhood who commute to the city each day. So we know people who commute to New York City. So we're going to investigate this because we're interested in our neighborhood. What's the average commute time for our neighborhood? Is it similar to what this article said, or is it longer? This is important. This longer is telling me, maybe there's a greater than symbol somewhere in this problem. Just keep that in mind. We survey a total of 21 commuters in our neighborhood. We're actually doing this, the 21 commuters. This is our sample. Okay, now every time you see a sample, you're going to be given what comes from the sample. Well, what happens? From our sample, we get an average commute time of 39.2 minutes, X bar. And our sample has a standard deviation of 10.3 minutes, little s. The sample standard deviation is that little s. Okay, so from here, we can set up our hypotheses. Alternative. We technically don't need to do this for the problem, but I think it's a good setup so you can see things a little bit better. Mu, because we said X bar or mu, equals, now what average do we want to use? The one from our sample or the one that's being claimed to us for the bigger population? We want to use the one that comes from the bigger population. 35.9 minutes. What is the alternative? The average commute time for people in my community is, and now what do we do here? Why did I write an equal sign? No equal sign. We look back. Did we say we want to know if our community is different? Did we say longer, shorter? What did we say? Go back through. Oh, it was longer right here. So we want to know if the average commute time is longer than this national number. There you go. You got your hypotheses. So what do we do with this? We've got to set up this distribution, right? So we can grab the pertinent information. So we go back to the distribution. And again, we're in a one mean scenario here. So this is another one mean scenario. So then we put in the relevant information, 35.9 minutes, standard deviation from the problem. The New York Times article said the standard deviation was 9.8 minutes. And again, if we don't really have some idea of what's going on here with commute times, we can just say normal. If you've got an idea, or if the article gives you an idea of how these should be distributed, you can change this population shape. But for now, let's just say it's normal. I don't have a good argument or anything in the problem that tells me otherwise. Okay, let's go over here. What's our sample size? Well, we talked to 21 people. So it goes in here. Let's hit draw. All right, we get this first picture. We don't really care about that. We get our second picture. The mean is 35.886. Well, that's really close to what we saw here. That's good. So we've got our distribution. So let's grab that and bring it over. Okay, so we've got our distribution here. That was our part A. So then we're interested in trying to set up our picture. Right? So we want to know, in terms of standard deviations, kind of how does this picture get set up? So we draw our nice normal curve. Not sure what happened right here, but that's fine. Don't worry about it. We set it up 0, that's the mean. 35.886. Just going to round here, 35.9. You can keep the 3 decimal places, but you can also round. So then what do? We go 1 standard deviation and 2, and then we go left 1, down 1 standard deviation, down 2. And so our goal is just to find out what these numbers are. And it works the same every time. Mean plus, we'll do 1 first, plus the standard deviation. Again, these are coming from the distribution, not the sample, not the population, the distribution. Very important. 35.9 plus 2. I'll round this too. We'll round here. You could try this out not rounded, keeping the 3 decimal places, and see how close we get. So I'll do this, and I get 38. Put it in. Okay, now go 2 standard deviations. So you could just take where you were and add another standard deviation if you want. That's fine. 40.1. All right, go the other way. Minus 1. So that's my middle minus a standard deviation. Okay, so that's going to give me 33.8. And now go 1 more down. 33.8 is where I was. Take away another one. That's going to be 31.7. There we go. We've set it up. This is 2 standard deviations. If we were back in chapter 1, I would have had you thinking about this box, right? The 95%, the 5%. So this is just all chapter 1 ideas. Okay, so then we would have said, okay, well actually, why don't you go calculate my standardized statistic for me? So we have our X bar. We can do that here. So our standardized statistic, how do we do this? Well, we follow the formula. Stat minus mean over standard deviations. Standard deviation, only 1. So that was what? What was our statistic? 39.2 minus our mean, 35.9. Again, I'm just rounding here, over 2.1. So before you even calculate this, think about it. What should this number look like? Where is it on this picture here that I just set up? Well, 39.2 is in between these 2 numbers. So just take a guess at this. Don't calculate it yet, just take a guess. I'm going to guess, I promise I haven't done this, I'm going to guess 39.2 is, let's see, 1.5. I'll just say 1.5. I don't know. 1.5 standard deviations above. So that's my guess. Let's try it. Let's try it. 39.2 minus 35.9 divided by 2.1 is 1.57 rounded. So not too far off. So that tells me that if I want to go find my statistic, all I have to do is start at the middle, go 1 jump, and a little over a half jump. This is my statistic, my X bar. It'll be right in there somewhere. That's in between -2 and 2, right? That's in my box. So that is a usual statistic because it's inside that box. And there you go. We got it. So the process hopefully is not too bad to kind of set this up. So let's check out that last one. Okay, so number 7, very similar to a previous problem. Same idea. We're looking at these poverty guidelines. The website, census website, gives 10.5% of citizens living below the poverty line in 2019. The last problem that we did this in, it was 2018 data, but it's still very similar. we're doing a very similar thing here, right? So we can steal kind of what we did previously with this is a pi x bar problem, our hypotheses we can set up, the proportion of people, but this time we're focusing on Mississippi, the proportion of Mississippi residents who are living below the poverty line, is that equal to the national average, right, of 10.5%? Or on the other hand, right, on the other hand, is pi, well, let's see. A study is conducted to determine if that proportion is representative of Mississippi residents. Doesn't say anything here about less than, greater than, so we're just going to say the alternative is it's not the CDC big United States number. So we got that down. That's our comparison. And we know our p hat is out of the 1,843 residents, 361 were below the poverty line. So what do we do for this one? We go to the applet. Right, we're at the applet. Okay, what's our sample size? 1,843. That's how many people we talked to. Let's get 1,000 samples. We got the picture. Take this, bring it back to the worksheet. So we've got our distribution here. What do we need from this? The mean and standard deviation, right? Because what's our point here? We want to try to make the picture our normal distribution, and we want to pick out the values that are 1 standard deviation away, 2, and then go both directions. 1, 2, -1, -2. Okay, so what's our mean? 0.105. So let's do the calculations. Go up 1 standard deviation. We can do that. Go up a standard deviation. Okay, so 7, that would be 0.112. All right, go up another one. 0.112 plus 0.007. That would be 0.119. So I'm just jumping. Go up, up. Go the other way. -1. 0.105 minus 0.007. Okay, this would be 0.098. Okay, do it again. Go down one more. 0.098. Go down another 0.007. This would get me to 0.091. So just start at the middle, go up, up. That gives me the 1 and 2. Go down, down. That gives me the -1, -2. Okay, let's go find our statistic. What was it again? 361 out of 1,843. We're going to have to plug that into the calculator. 361 divided by 1,843. 0.196. Rounding it a little bit, 3 decimal places. Go find us, 0.196, and nowhere near. We are nowhere near this value. So we're many, many, many standard deviations away. Let's be specific though, because we can figure it out. But just looking at this picture and comparing, no way, not even close. So that's my intuition looking at it. Then I'm going to get a big number here. Well, let's check it. Take your statistic. 19.6. 0.196 minus the mean over the standard deviation. 0.007. Okay. So we're going to put this into our calculator, and we're going to see what we get. I'm thinking it's going to be a big number here. We'll see. Minus 0.105. You try it too. Divided by 0.007. Whoa! 13. So what is this crazy number telling us? This is telling us that this statistic we actually got from Mississippi state residents is 13 standard deviations above the mean. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm off the screen. So extreme. Crazy extreme. This is screaming at me that no way does the Mississippi state residents have the same level of poverty as what the census is telling us is true for the United States. This makes me feel like Mississippi is definitely not the same as the United States and the whole U.S. in terms of the percentage of citizens below the poverty line. Do we know exactly what the number is? No. We just have some pretty strong evidence it's not this national number. So you get something this big, that's way outside the 2 range, 2 below, 2 above, and so the statistic is unusual. All right, and then number 8, there is none. Get out of here, number 8.